Okay, so this is our next video on differentiation on derivatives for Math 1560 Calc 1 at U of L for the fall 2017 semester. And in this video we're going to explore one of the uses of the chain rule, which is called implicit differentiation. So implicit differentiation involves equations where basically you have functions of both x and y. So you have some equation relating the two variables where you can't necessarily solve for y. So a simple example being the equation of a circle, right? X squared plus y squared equals 4, right? We know what that gives us. That gives us a circle centered at the origin of radius 2. Okay, terrible circle, but you get the idea, right? So a lot of these equations, you'll notice, don't necessarily define functions, at least not everywhere, right? Because we can see that, the circle does not pass the vertical straight line test, right? So it can't be the graph of a function because for most x values there is more than one y value, right? If I put x equals, say, 1 into there, y could be either plus or minus the square root of 3. So I get multiple y values for a given x value. I don't get a function. But of course there are pieces of the circle that work. If I took just, say, the top half of the circle, right, I only take, so if I take x squared plus y squared equals 4, and I require that y is bigger than or equal to 0, okay, then I do get a function. I get this function here, the square root of 4 minus x squared, right? And so sometimes by taking part of the curve that is defined by an equation like this, so I don't take the whole curve, I just take part of it, I can define a function, right? So this is what we mean by an implicitly defined function. We might not have a curve which is globally the graph of a function, meaning the whole curve isn't necessarily a graph, right? The whole circle is not a graph. But locally it might be if I just take part of the curve, right? If I take the top half of the circle, I can think of that as the graph of a function, right? Of course, I could also take the bottom half. The only thing I really couldn't do is I would not be able to take any piece of the circle that passes through these points on the side, right? Anything that passes through the x-axis, that's not going to define a function, because for every x value that for every y value here, I have a corresponding one here, corresponding to, where the same x value gives me two different y values. So I can't take a piece like that. That's not going to give me a function, but I could take the top half, I could take the bottom half, and I would get a function. One of the things that you can kind of get a feel for if you kind of dig into this a little bit more, and this is something you will see in probably Calculus 2 if you go there, is that the places where you don't get a function, it's very easy to identify the parts of the curve that don't define functions. They're exactly the parts of the curve where you have vertical tangent lines, right? And you can see that the tangent lines to the circle at the two ends are vertical. If you stay away from those places, you can write y as a function of x, at least for a portion of the curve. So this is the idea of an implicitly defined function, and what we want to do is we want to be able to take the derivative of such a thing. And now one thing I could do, of course, I could say, well, this f of x here, right, f of x is, this is 4 minus x squared to the 1/2, and I know that if I do chain rule combined with power rule, I could take this derivative. So just to save time, I'm gonna jump right to the answer. So we take the derivative of the outside function, the square root function, right, evaluated at the inside, and then we remember that we have to multiply by the derivative of the inside, which is 4 minus x squared, and that gives me minus 2x. But actually, with a bit of simplifying, I can write this as minus x over the square root of 4 minus x squared. And so if y is equal to f of x, if this is my y value, then really what I have here is minus x over y, right? And what implicit differentiation is going to let us do is implicit differentiation is going to allow us to come to this final result here, this minus x over y, which gives us the value of the slope of the tangent line at any point on our curve. Implicit differentiation is going to let us find that without having to first solve for y. This is really what comes in handy, because for some of these equations it might be difficult to solve for y. Here, it's messy, but it's not impossible. But it's not too hard to come up with examples where the algebra involved in solving for one of your variables in terms of the other is difficult, if not impossible. But we'll see that we can still compute the derivative even if we can't solve for one of our variables. So how does this work? Well, the way you do implicit differentiation is you take the derivative of both sides of your equation, keeping in mind that you're treating y as a function of x. So let's kind of spell out, let's do this kind of, where we say, so we suppose y equals f of x. So let me put everything in terms of this f of x so that we can kind of see how things will work in terms of the chain rule, and then we'll back up and we'll see how we can kind of do things a little bit faster. So this tells me that what I have here is x squared plus 3 times f of x. That's squared. Let's fix that. F of x is being squared, right? Y is equal to f of x. I see a y squared there, and then this whole thing is squared. And then I have 4x times f of x, right? And so now I take the derivative of both sides. So these two functions are equal. That means their derivatives must be equal. And what do we get? So on the left-hand side here, right, I can think of this as, I can think of this whole thing here as being like u, right? So this is like u squared. So the chain rule says what? I should have 2u and then du dx. Okay, and so let's just kind of let's take that and set that aside. So put that over here. So 2u du dx. That's what we're putting here, and let's actually write out what that is. So what was u? U was this inside here. So it's 2 times x squared plus 3 times f of x squared. Okay. And then I have to take the derivative of the inside. X squared plus 3 f of x squared. On the right-hand side, I've got a product, right? X times f of x, so I should use the product rule. 4 times the derivative of x, which is 1, times f of x, and then 4 times x times the derivative of f, so simply f prime of x. I've got one more derivative to take on the left, so let's put that in. So the derivative of x squared is simply 2x. Now what about the derivative here of 3 times f of x squared? Well, the 3 comes out, and power rule says the 2 comes down, so I get 2 times f of x, right? Times, what do I have to still put? I have to take the derivative of the inside. I have to take the derivative of f of x, so I get f prime of x, and my right-hand side is still the same. Okay. It's a big mess, but we're making progress, because what we can do now is we can solve for f prime of x. We can collect up all the terms with f prime of x in it. So how does that look? We go f prime of x times. So what is multiplying f prime of x on the left? I've got f prime of x times this guy, but then also times all of this out front. So what do I have? I have 3 times 2, which is 6 times f of x. Let me kind of combine things here. So 3 times 2 times 2 is 12. You guys can maybe, write everything out here carefully, double check my algebra, make sure that you're convinced, fill in the steps here. You guys can do that on your own. Okay. Well, oh, but now that's not all I have for f of x. That's the stuff that multiplies f prime on the right hand side. But I also have this 4x f prime of x on the left. So what do I need to do? I need to subtract 4x f prime of x from both sides, and I get something that looks like that. And what am I left with? I'm left with this 4 f of x, okay, times, well, what do I have to multiply by? I've got to multiply by 2x. So this is the stuff that doesn't have an f prime in it. So if I multiply through the brackets, I have 2x times 2 times this whole thing. So I have, so 4f of x times, I don't know why I have a bracket there, minus, so I got to subtract off 4x, that's 2x times this 2, right? So the 4x is this times that. That's my 4x times this term here. So I have x squared plus 3 f of x squared. Okay, well, that's a mouthful, and we're not quite done. What do we do from here? Well, let's squeeze in one more page. I think I can do that here. Let's add a page in. Oops. Okay, one new page. All right. So what do I have to do? Well, all I have left to do is solve for f prime of x, but that means to solve for f prime of x, I just have to divide by this whole mess here. So what do I get in the end? I get f prime of x equals, what was my numerator? This part here, 4f of x minus 4x times x squared plus 3 f of x all squared divided by, what's my denominator? 12 f of x times this bit here, so I get 12 f of x multiplied by x squared plus 3 f of x squared minus, and there was a minus 4x there. Okay, and then you're done. You've solved for f prime of x, right? Now, that's a bit of a mouthful. How can you do this a little bit faster? So the way you do it a little bit faster is, if we go back to the beginning, we don't really bother to make this substitution, right? So we're assuming that y is defined as a function of x, but we leave this, as the name suggests, we leave this implicit. We don't actually plug it in. But what that means is when we take the derivative of both sides, whenever we see a y derivative, when we take the derivative of something involving y, we need to multiply by f prime, right? So think about like what you have down here, right? Look at this term, right? Where did this term come from? This term came from taking the derivative of this, which is 3y squared. So what do I get? I get my 3, the derivative of y squared, 2y, but then chain rule says I need to multiply by the derivative of y. So y is a function of x, so I get that extra derivative term. So the way this looks is you start with your equation, x squared plus 3y squared squared equals 4xy. You take the derivative of both sides. Okay? And so the first thing I have to do on the left is I have to do the chain rule. So 2 times x squared plus 3y squared times the derivative of the inside. Okay? X squared plus 3y squared, and save this derivative for the next step. And now let's take the derivative, the derivatives we have left on both sides. X squared, 3y squared, and here I get 2x. Now, the derivative of 3y squared should be 6y, right? But remember that we're thinking of y as a function of x, and we're taking the derivative not with respect to y, but with respect to x. So that f prime, that's a dy dx. So every time we take the derivative of something involving y, we need to throw in this dy dx term. Okay. On the other side, I still think of this as a product, x times y. So I take the derivative of x, I get 4 times 1 times y, and then x times the derivative of y. What's the derivative of y? dy dx. Okay. Now, let's kind of expand things out here. So this is going to be, if I do the 2x times this whole thing, I get 4x times x squared plus 3y squared plus 12y times x squared plus 3y squared dy dx equals 4y plus 4x dy dx. And now I can collect up my dy dx terms, and if you want, you can just call this y prime, save yourself a little bit of writing. 12y x squared plus 3y squared minus 4x equals 4y, subtract 4x times x squared plus 3y squared, and therefore my derivative dy dx is 4y minus 4x times x squared plus 3y squared divided by whatever is multiplying dy dx, 12y times x squared plus 3y squared minus 4x. All right, so it's a bit of work. It's kind of messy, but you get to the answer in the end. You get your result, and notice that it's a result involving both x and y. So now, if I wanted to find something like the equation of a tangent line, I'd have to find a point on the curve, get both my x and my y coordinates, plug them into this mess to get the slope of my tangent.